Okay, welcome to the section. This afternoon we have three speakers. Welcome to the first one, the Professor Pehlevan from Harvard University, and his topic is building sensory representations for the education.
Thank you. Okay.
Just tell us a few jokes.
Oh yeah,
Yeah, there are a few people coming
I
up.
did not understand. Okay. Well, thank you for the invitation. I've been at Harvard for maybe 8 months now, and this is my second time here already giving a talk. I look forward to more invitations. Please do invite me. So what I want to talk about today is basically two projects that's going in my group. So I'm in the applied math area here in the School of Engineering, and my research is in computational neuroscience. And I want to describe two projects which maybe describe two different approaches to this kind of field. One, I'll say more data first. So I'll describe a problem which is motivated through a direct experimental observation and our efforts in modeling results. And the second one is more a bit more theory first kind of an approach, motivated by general observations about how brain learns and describing how such learning can be efficient, all of it in the context of learning. So that's a lot of my research is in this context of learning. So first I'll describe to you basically an experiment which points towards evidence in learning in olfactory cortices, and I'll describe you why this might be a bit surprising. And then I'll describe to you a theory which tries to explain how such learning can be actually efficient learning. And here I'll make comparisons to machine learning. Okay, so let's start from this left side of the picture, and this is a collaboration with Venki Murthy's lab here. Okay. So the question that we want to ask is about the nature of connectivity in sensory cortices and how they are shaped with learning. So there are some observations here. So if you look at most sensory organs in mammals, you'll find that they project to the brain in a structured and ordered fashion. So these are described by words like retinotopy, or in vision, tonotopy in audition, or sensory homunculus in touch. And basically the idea is, there's some kind of spatial topography in how sensors are organized. For example, in your retina, there's a photoreceptor array, and that spatial topography basically gets conserved to some extent the way they always project to cortex. So nearby areas in the cortical surface might be getting inputs from nearby photoreceptors. Okay. Now, there's one exception to this. That's olfactory cortex. Now, people have been looking for some spatial topography and projections from the olfactory bulb. So that's like the first layer of processing, depending on your count, maybe the second layer of processing of olfactory information, the olfactory cortex. And they haven't really found it. So this is basically a sort of a cartoonish picture of how the olfactory cortices works. So these are the nostrils. I'm going to be talking about rodents or rats. These are basically olfactory epithelia, olfactory receptor neurons. They project to the first layer of processing the bulb, and the bulb basically makes projections to the olfactory cortices. This one is piriform cortex, and there are several areas there that are important. Anyway, so what's being shown here are basically axons. Okay, this is basically of this nerve fiber, and their projections to the olfactory cortex. The message that this picture is trying to show is that there is no structure. Right? So it seems like, an axon might be projecting to neurons all over the cortex. Okay. Now this is interesting. So one question you might ask is, of course, why such, and theorists use the word random to describe such connections. Why such random projections might be important, and people use ideas from compressed sensing and things to make sense out of this. The other thing I want to describe, I want to describe today, so I'm going to go not here, but there's another kind of projection here that's important, and that's basically interhemispheric projections. The idea that how left and right side of the piriform cortex coordinate or compare information, right? And this is interesting in olfaction because of the following. So this picture is accurate in the sense that when you smell from one nostril or the other one, the first time olfactory information about the two nostrils meet is at the level of cortex here. Right? So the nose is separated by a septum. So the odorants are basically confined in the nasal cavities in the left and right side of the rodent, right? When they go to the next stage of processing, they don't mix. When they go to the cortex, they don't mix. Only at the level of crossing the hemispheres, where such information from both sides of the nostrils might be coming together and merge and coordinate. So the question arises then, if it is true that there is no spatial topography here, if everything is random, whatever that means, right? How can we actually align or coordinate information in this side versus that side? So that's a question. But this is an interesting example of what happens when your nose is congested, right? One side of the nose or the other side of the nose gets congested. There's no airflow. So you're getting odorants from one side or the other side. How do these coordinate? Is it truly this structure or random connectivity when you're crossing cortices? That's the idea. Exactly. So the same thing. People have looked at basically these connections and have found no spatial topography. People have used the word random to describe such connections. Now we're going to look for structure or randomness when you're crossing from one side of the brain to the other side. Okay, that's the problem. All right. So a lot of the work has already been done in this by our excellent and brilliant experimental collaborators, especially Julian from Venkimurthy's lab. And he designed this brilliant study. Okay, what he did was the following. Well, they put basically an electrode on the prefrontal cortex on one side, and I'll call this the ipsis side, meaning that's where the electrode is, and everything is going to be defined based on this. Okay, and then they designed a mask. They put it on the rat's face, such that they could control which nostril an odorant goes to. So they'll give an odorant from this side, okay, and then because of the mask, they can also present an odor from the other side. And there's no mix in between them. So if you're presenting the odor from this side, the information goes to your recording device directly from this tract. And if you're presenting it from this side, it goes through this path and crosses the corpus callosum to go to the other side. Right? And what we're going to do is we're going to compare representations here. By representations, I mean firing rate of neurons or responses of neurons to odorants coming from this side or that side, and try to see if there's a correlation between them. Why correlation? Because if everything was random, meaning there's no structure, just neurons are connected to each other by chance, right? The prediction of this will be you shouldn't be seeing any correlations in the responses of neurons, right? When comparing odorants coming from one side or the other side. It's a very simple prediction. There isn't even math here, right? Okay. So this is real data. Let's look at if that's true. Turns out this is not true. So each line here, so it's a matrix. You're looking at a particular area, AON. All right? So I have 10 neurons in this case. This is a parallelogram. And the x-axis here are basically odorants. Right? So you're seeing 15 or 16 odors and 15 or 16 odors. Right? And this is a color code. It's basically denoting the response to an odorant with respect to a baseline. So some neurons are activated to let's say, neuron 1 is active for this odor and not active or deactivated for the other guy. Right? So this side is responses with respect to an odor presentation from one nostril, ipsis side. So the information just went directly from here to there. And this one is due to odor presentation from the contra side. So the information went from here, and then crossed the corpus callosum. Right? So if it was random, we should be seeing no correlation among these kinds of matrices. But if you just do a very simple analysis, right, you just basically take each pixel here and put it on a scatter plot. So you would call this a scatter plot of neuron odor pairs. Actually you see a big correlation. So the random model will suggest this zero correlation. So this already suggests there is some structure here. If everything was scrambled, you wouldn't have to see anything. Right? So that's great. So we took this data set and helped them doing this analysis and sort of digged a bit further. So here's another analysis we did. We took these recordings, okay, and we'll take them from the ipsis side, meaning the same side that the odor is coming from. And we basically train the linear decoder to tell which odor it was. Right? So there are 15 odors. You're going to look at a huge vector of neural population activity. Each element of this vector is 1 neuron's firing rate. We have about, like, I don't know, 300 neurons or so. Goes through a linear classifier and gives us basically which order it is, 1 over 50. And of course, as I saw, this is trained on the ipsi side. When we test on the same side, as a function of the number of neurons you have, you're seeing basically you're getting very good accuracy. And this is basically chance level over here. So we have 15 orders, that's 1 over 15. Now we're going to take this decoder and test it on the orderants coming from the other side. So we train on the ipsi side, but we're going to ask if we can decode information coming from the other nostril. So that's basically a test of saying if there was another neuron looking into this population, would it be able to tell if it's the same order regardless of the nose side, right? And it turns out basically you get very, very good performance almost at the same level within levels of chance. So basically, decoding works left or right in this cortex. Orders are aligned. Okay. Now, the next thing we are going to do, we're going to try to explain this in a mechanistic model. And I'm very proud of this model because this model is going to have a very simple things in it, no big deal, and just 3 parameters. And I'm going to test 5 things, this 3-parameter model, on 5 things that they're not fitted on. It's going to work beautifully. And this is something very rare happens in the kind of business side, in computational neuroscience. The data is usually very noisy, simple models don't work or don't fit anything. But here it actually works. And the model goes as follows. So we're going to take this random projection idea like to heart and model basically responses of neurons sitting in this olfactory cortex in response to the inputs, which is coming from the olfactory bulb, by basically a random projection. So I'm going to take this vector, multiply it by a random matrix that's Gaussian distributed, and threshold it. That's going to be my model for producing responses on this side. So this has 2 parameters, basically this variance over here and the thresholding. Right? Technically, I'm using a shrinkage function, so it's not a ReLU, but it has this kind of thing. And the responses from the contrast side is going to go through this extra sort of processing. I'm going to have again the same random projections over here. Okay. This is again basically a Gaussian random matrix multiplying this, some thresholding. And then I'm going to cross corpus callosum, and that's this line. Then I'm going to introduce another parameter over here.
What is lambda? Sorry. What is lambda?
Lambda is the threshold over here. So it's a shrink function. Sorry, I should have put this. So the activation function looks like this. So this is lambda.
So why theta and lambda, they aren't redundant, right?
Theta, what is that? You want sigma and lambda?
You can scale.
So, okay, so there's 2 parameters here,
Yeah.
and I'll show you why. So one of them is going to set, in the next slide I'll tell you about how
Okay.
they fit. So one of them is going to set the scale of all of this thing, so meaning like the units here, what hertz in hertz, and the other one is going to scale basically what percentage of neurons are firing. I have a slide exactly about this. And the second one is basically this kind of crossing. So this has 2 parameters. Sorry, this has 2 functions, so 2 components to it. One of them is again this random component, which basically is the Gaussian thing again. And I also introduce a structured component to this. So this structured one is basically generated from responses in the model. So I look at the responses here in response to a particular order, and responses here in response to a particular order, and I try to align them using a neuroscience-inspired learning rule. So this is not backpropagation or anything. Okay, this is called Hebling rule or a covariance rule. What it does is, let's ignore this. So mu here stands for basically an orderant index. So C is for contra. J is the neuron's index. It's looking at a correlation between a jth neuron in contra side and ith neuron in the ipsi side, and try to build a matrix that basically correlates these responses. So if you're familiar with Hopfield networks, very similar neural learning rules go in there. Okay, so that's it. So this alpha equals to 0 is a purely random thing, and alpha equals to 1 is a purely structured thing. So we're going to vary this parameter and see how it fits. All right. So coming to the fitting of this, I just want to show you what's going into it. So, we're gonna take this from data. These are neural recordings, and there's sigma and lambda. There's 2 parameters here. I'm going to show you how we fit to this. Basically, we're going to fit it to the sparseness, meaning what percentage of neurons are active past this threshold, and there's the remaining overall scale. We're going to set this to the overall firing rate, okay? And there's a one parameter here, alpha, which is we're going to fit to this correlation coefficient we saw, okay? So 3 parameters, I'm going to fit the 3 values, and I'm going to show you 5 different tests which does not fit, right? So this is about what you were talking about. So how do we fit the sigma and lambda? This W is random. So these are basically in the model Gaussian distributed. So this is basically a histogram, a picture of basically inputs to neurons across all mu and I indices. Right? So this lambda, this width is basically related to the sigma, how W is distributed, and this lambda is basically this threshold function. So basically, the ratio of these guys is fit to, an experimental value, 20% sparseness, which is the ratio of neurons which fire. That's it. And I was saying the scale, overall scale, is fit to the axis over here. So, okay. So this is the fitting procedure we do, and this is just 3 different sort of population metrics that we get from data that are interesting for neuroscience reasons, and we see how the model does in this. Okay, so what this one is showing is basically response magnitude as a function of the percentage. It's basically a histogram of what neurons firing rates are. Okay, so remember we fit this value, right? But we didn't fit the shape of this tail. It was just Gaussian. So this is the one place where we don't do well, but it gets the overall trend right. So this is basically the number of orders a neuron is responsive to. Neurons do not respond to all orders, but they cross this threshold for some number of them. So you get the trend right, and good fit. And this is a sort of a very interesting measure. It's called a positive-negative balance. So this is an observation on the piriform cortex again. If a neuron gets positively activated to an order, it turns out most of the time they are positively activated for most of the orders, right? So, and if it's negatively activated to an odorant, meaning it decreases firing rate with respect to a baseline, that's almost true for almost all odorants. So this balance can be turned into a metric, basically how much you're biased towards all positive versus all negative, and the blue guy is that distribution, and this guy is coming from this simple Gaussian thresholding model. I mean, depending on which field you come in, this might look not a good fit for you, but I mean, in neuroscience, this really rarely happens. Right? Just a Gaussian threshold, it explains a lot of things like this. Okay, what about that alpha parameter? Now, I'm going to look at 3 different things here. I'll tell you what they are. And I'm going to vary this alpha parameter. And what's being shown in this in green is the experimental range of these 3 metrics. And the point I want to make is there's a few, let's say, or a range of values of alpha which stays in the experimental range for all of these things. So you can think of one of them as fitting and the other 2 as test. So the first metric is basically the number of bilateral correlated units, meaning I look at each, again, this was the matrix I showed you, I look at each of these rows, each neuron as a function across orders, and I correlate them, right? With a Pearson correlation, because there's a finite number of orders, I get some are correlated, some are not correlated. There's a particular percentage. If you keep increasing alpha, meaning all the way from random to all the way from structured, you expect this to get increasing. So that's what you see. This is the experimental range. Experimental range here refers to multiple different animals. So for some animals it's here, some animals it's there. There's a range. So this one is about this particular correlation metric I showed you, the Scatterplot. It basically looks at this slope. Again, there's an experimental range. As you increase alpha, you expect this correlation to increase, and there's again a range, which fits sort of inside the experimental range, and there's a value of alpha that stays inside there. And this one is about the decoding accuracy, where we're doing the hard one. We're training on the ipsi side and testing on the contra side. Okay, and again, as a function of alpha, this is the chance level. You increase, meaning the more structure you have, the more aligned the responses are. So again, this is the experimental range, and there's again a function of there's an alpha value that sits basically inside this experimental range. Yeah. So, okay, what's the story here? Right? So this alpha is not equal to 0. So that's the message over here. So to conclude, out of all of this study came, I think, some very strong evidence for structured interhemispheric projections in the olfactory cortex. And as I told you, this is somewhat new because people previously looked for structure in olfactory cortices, not in this particular part, but the projections from bulb to the olfactory cortex itself, and did not find any special topography. And it sounds like basically this particular experiment and analysis shows that there is such projections. And the second thing that comes out of our modeling effort, that such structure can be learned through basically simple Hebbian mechanisms, right? The way I did these structured connectivity was through a very simple Hebbian learning rule, and it seems to get us to a parameter range where you can actually, fit this data to a reasonable manner and explain all of these things. Okay, so this concludes the first little story I want to tell you. It basically looked at data and sensory cortices, and then came to the conclusion that Hebbian mechanisms can explain some structure possibly coming through connectivity and how learning might be happening with such connectivity. Okay. Now I want to switch to another story, and that basically picks up on this Hebbian learning idea, okay, and learning idea. And this one is basically the more general question of how representation learning is happening in the brain, right? And the setting here will be very simple again. So we'll think of stimuli, let's say, and for this particular one, I'm going to talk about, give examples from the visual processing, right? That's n-dimensional, all right? So you take this, I guess it's a picture and concatenate into a dimensional vector. And you show it to an animal or us, right? In our brains, there's a population of neurons. In response to this, we can take this population and take defining rates of them and make it into a k-dimensional vector and call this population activity. So this is what I will mean by representation. To each stimulus, there will be a representation, a k-dimensional representation. So the question, of course, is like how such representations are learned. What is a good way to learn? What is the target of learning should be? The particular question that I want to ask is, how would you learn it efficiently? How would you learn it efficiently, especially with Hebbian plasticity? Why is that a question? It's because of the following. And to make this sort of more explicit, I want to contrast the Hebbian learning idea, which I introduced in the previous slides, to how we learn machine learning, especially the backpropagation algorithm. Okay, so this is supposed to be a picture of how the brain's hardware, and this is supposed to be a picture of deep net, right? And the idea goes as follows. So let's look at here, right? So there's sort of two ideas here which make this whole learning efficient. Right? So one idea, of course, you come up with, well, maybe three. You come up with an architecture, that's idea one. And then you define a goal, that's a cost function. Right? So it should be a meaningful goal. Right? So that basically says the whole circuit is a goal. And then efficiency or efficient learning is basically this idea of gradient descent. Right? So there you just give it an input, get an output, calculate a cost, and take a derivative. And this derivative is in some sense optimal because it's pointing towards the direction of maximal sort of descent. Right? Now, there is another concept, that's locality versus non-locality. Right? So if you do this for such a network, and if you try to calculate what this gradient descent gives you for, let's say, this particular synapse, right, you're going to get an algebra. It's going to be a big expression over here. And that expression is going to depend on a lot of things that is not just available at the synapse. Meaning, to be able to, this connection. To update this connection, you'll need information from maybe these connections, activations of these neurons, and so on and so forth. That's why you will need a lot of non-local information, and by non-local I mean local to that particular connection. Now, why is this a problem for biology? Right? So think of a synapse sitting in the middle of your brain. Right? It has very little information about the global state of the neural of the network that it sits in. Right? There's not like a global bus or something that's bringing all this information to you. Right? It maybe knows about this presynaptic neuron state, postsynaptic neuron state, maybe nearby things by some synaptic boutons leakage and stuff like this, but not all the neurons that's downstream of you or something like this. So Synapses in the brain are uninformed. Right? They don't have all this information. And from this point of view, it's actually interesting how the biology can be learning, because basically the situation is the following. So you have all these agents which are uninformed about the global state of the network, and they don't know what each other is doing because there's not like these communication channels. Yet they are able to communicate in some way and collectively basically do some collective behavior, which is learning. So that's hard. Okay? In artificial neural networks, the way you solve this is through algorithms like backpropagation, which basically backpropagates all the information that you need from all the way here to that particular connection. Right? So there is no analog of such thing in biology. People have been looking forever, never came. Okay? So just to make sure we're on the same page, in notation-wise, X is going to be the activity of a pre-synaptic neuron, so that's the neuron before the synapse. And Y is going to be the activity of the postsynaptic neuron, that's the activity of the synapse after the neuron after the synapse. And by local, I mean an update rule that depends on just these variables. The presynaptic activity, postsynaptic activity, and synaptic data itself. The particular rule where you correlate these things is called heavy. Okay. So the question I want to ask is, so there are these two great ideas here, cost function and gradient. Are they not existent for this side? Right? Because you want to keep those guys because these seem to be, cost function defines a global goal. That seems like a good thing to have. And gradient is basically a measure of efficient learning. Right? That's a good thing to have. But this Hebbian or local learning seems to be inconsistent with those big ideas. So what's happening? Is the brain not efficient? Or if it's efficient, how is it doing it? Can we formulate its efficiency through these ideas? Okay. And the particular context I'm going to ask this question is going to be this. So now I'm describing another problem. Okay, so I'll merge them together in a second. And this is the problem of visual object recognition. Now this problem has been posed in terms of manifold learning by many different authors. Sungen Lee, DiCarlo and Cox, and James DiCarlo later on again. And the simplification of the problem, it doesn't address everything about it, but it gives you a good mathematical framework within which to address it. Okay? So let's go with it. So what is the idea? The idea says, think of an image of an object falling onto your retina. Now, that's an activation pattern for your photoreceptors. Each of your photoreceptors are basically giving some signal out. So let's think of a space where each coordinate is basically a photoreceptor activation. So image of an object falling onto your retina in this case is a point. Image of a different object is a different point. Now you start, let's say, varying this object. You get all natural variations. This object might be moving into your visual space, might be rotating around, so on and so forth. And all these natural variations trace a manifold on this space. Okay, so I'm using the word manifold in a very loose manner. Think of it basically a data cloud. Okay, if this is a continuous motion, this will be a connected thing. Okay, that's the idea. And a different object is a different manifold. Right. So then the problem of object recognition can be thought of as follows. Right. Well, I have to give you one more information, and that's the following idea. So whatever is doing the classification in the brain, let's say is a neuron, and neurons are to first order perceptrons, they are linear separators. Right? So the best they can do is put a separated hyperplane in this space. Right? So then the problem of object recognition is basically a linear separation of these manifolds. This seems like a very high-dimensional space. These manifolds are presumably low-dimensional. How many transformations of these objects can you think of? So it should be a solvable problem. It turns out these manifolds are actually not linearly separable. I mean, people have shown this in simulations in pixel space. It's interesting why that happens. I don't know. But that's a fact. Then, given this fact, people have proposed that what the visual cortex must be doing is to go from this representation to another representation. Right? So you take these manifolds and warp them in some way, okay, such that they become linearly separable. So this was basically photoreceptor space. This is perhaps happening. The axes here are basically firing rates of neurons in some high visual cortex. And in this space, basically, if you vary these objects, manifolds vary in such a way that they are linearly separable. So So the goal of visual processing is to go from here to there. So that basically tells you how you what you should be doing. Now the question that I'm going to ask, and I was talking about Hebbian learning, okay? Can actually Hebbian mechanisms do this, right? Go from here to there, right? So I'm not going to fully answer it, but I'll present you some steps. Now, looking at the anatomy of the visual cortex, actually these authors came up with a final hypothesis of how this should be happening, and causing pictures like this, okay? So, there are people have been looking into the structure of visual cortices, and you find basically there are some, at least, circuits that seem to be repeating in the sense that the anatomical features of local circuits in the visual cortex seem to be repeated, right? So based on this, and based on the hierarchical structure of the brain, so the Jim DiCarlo and colleagues have come up with the following hypothesis of how this should be working. Stimulus comes in. You are basically you're in one layer of the brain. You have all these little modules, okay, that look at small and small patches of the visual inputs. And somehow, okay, these little modules are doing their local disentangling, whatever that means, and in their local portions of visual field. Just to give you an idea, in primary visual cortex, neurons respond to a patch of visual field that's the size of your thumb at an arm's length, okay? And somehow these guys coordinate among each other and then coordinate across layers, and at the end it goes entangled, comes here, disentangled. Okay. All right. And the final information I should tell you, if this is happening, it should be happening mostly unsupervised because we just don't get so many labels in our lifetime. Is this possible? So people said this, no one put any math into it. Now we want to see if this is possible. And to be able to ask this question, and this is where I'm going to make into the connection to efficient learning with Hebbian mechanisms, I'm going to look at the most basic biologically plausible unsupervised learning network that you can imagine. Okay, and I'll argue why this is the most basic one. Right? So it's basically a neural network with some lateral connections. So W is the feed-forward connectivity matrix. L is the lateral connectivity matrix. Okay? So there's some dynamics here, which is pretty standard, and there's some activation function, which is a value in this case. So the networks for each input goes through dynamics, comes to a fixed point, and produces an output. That's what it is. Okay? And the learning is going to happen in the following way. I'm going to introduce Hebbian learning for feed-forward synapses, the most basic biological update rule. So that's Wij, right? So the Wij update, so that's input from jth synapse to ith. So jth input to ith output is going to just be a function of jth input and ith output. And this is a decay term that makes the whole thing stable. Nothing special over there. And I'm going to introduce another, again, anti-Hebbian. I'll tell you what that means for the lateral rules, and let's ignore this for the moment. Okay. So what's happening over here? So let's first think of like the case where we had no lateral synapses. Everyone was looking at the same input, and everyone was doing the same update. Okay? Because of the locality of the learning rules, meaning that each synapse knows just about the state of input and output, there's no lateral connections. The synapses to this neuron has no idea what this neuron is doing, and synapses to this neuron has no idea what other neurons are doing. So they're just doing their independent thing. And because of that, they'll all actually be learning the same thing, because they have no idea what each other is doing. Actually, you can prove or argue that in the case where I did not have this nonlinearity, everyone would learn to take the data and project it to this first principle component just because of this rule. Right? And that's not a rich representation. Right? You want a representation where people do different things. So to be able to do that, then what you need to do is you need to make these guys talk to each other somehow, know what each other is doing. And a biological way of doing it is through lateral connections. And then the way you should be doing these lateral connections is not Hebbian, because Hebbian makes similar things fire more similarly. If you want to make them fire differently, you want to make them anti-Hebbian, meaning you want to put a minus sign in the synaptic weight between them. So this is the argument. This is basically tells you that it's like the sort of the simplest and non-trivial learning network that you can come up with that operates with such learning rules. Okay. Now this turns out to be a very powerful machine. Okay. So the simple thing, what tasks can it perform? Okay. So there's a bunch of things. It can do subspace learning. It can do sparse coding. It can do clustering. It can do ICA, basically independent component analysis. And it can do actually manifold learning, which I'm going to go through. Okay, and all of this, I mean, it's surprising that one circuit, the same Hebbian learning rule, can do all of these things. Okay, and it turns out this is true because what it does actually, I'll show you that it actually efficiently optimizes a cost function, which I'll call non-negative similarity matching. I'll give it to you in a second. Okay, so this is basically like a matrix factorization kind of a cost function. It takes as input some data, and depending on the structure of data, it performs something, and that something can be interpreted as many of these things. Very much like you can interpret matrix factorization as some of these kinds of things. Right? So it's basically what this circuit is doing. All right, so what does this have to do with non-negative similarity matching? And this is the place where I'll make the claim that this is actually efficient learning. It's the following. So let's formalize the problem. I'll take basically some data sets, and I'll have capital T of them, right, n dimensions. And I want to learn a representation of it, meaning a vector, a k-dimensional vector for each of these data points. Okay? So I'll formulate a cost function for learning, right, which is the following. I'll go through all pairs of inputs and take their dot product, so I'll call their similarity. Okay? And I want to learn a representation which basically produces this as much as good as possible. So learn k, learn these y's, such that the dot products here match the dot products there. Right? And I also introduced a parameter alpha, which will be the role of which will be apparent in a second in the context of manifold learning. So nothing's complicated happening here. I just introduced a non-negativity constraint also because the finiteness are non-negative. Okay? So the other thing I want to say is in this cost function, actually, I'm not going to assume there's a network. Just inputs and outputs. The connection to the network is going to be apparent in a second. Right? So input similarity, output similarity, match it. This is a meaningful cost function because, for example, if you do not have this non-negativity constraint, you can analytically solve it, and you can prove that optimal solution to this will be take X and do PCA on it and project it to the principal subspace, and so on and so forth. There's also an independent component analysis interpretation of this, which I'll not give you today. Okay, but I want to talk about its properties in manifold learners because that's the problem I was talking to you about in terms of vision. All right. So what does this have to do with manifold disentangling? All right. So here's the idea. And again, I'm using the word manifold in a very data scientist sense. It's just basically a cloud of points. That's what I mean by it. Okay. So it all depends on parameter alpha. So the following is true. Okay. So take any data set. It can be uniquely clustered such that nearest neighbors, okay, within a cluster have greater than alpha dot product, and any 2 points that belong to 2 different clusters have less than alpha dot product. Right. So let's just make sure we're on the same page. This is supposed to be a sort of a picture of this thing. This red and blue guys are supposed to be 2 different alpha clusters. Okay? So any 2 points that's next to each other here have greater than alpha dot product. And any 2 points across blue and red clusters, maybe this guy and that guy, has less than alpha dot product. Okay? That gives you a unique clustering. All right? Now, and because the comparison is between nearest neighbors, these manifolds can be, or these data clouds can be entangled in the sense that they are not linearly separable. Right? So it's just, there's going to be a lot of complicated geometry happening here. So you can prove that basically in the limit that this k is large, and there is an upper bound on how large that should be. The learned representations are such that these manifolds are completely disentangled in the sense that a bunch of Y neurons respond to only red points, and a bunch of red neurons only respond to blue points. And there's just completely different subspaces. And the proof is not very hard, but just the motivation for it is here. Okay? So this is just alpha. Let's just look at a single pair. Alpha goes in here. Same thing. If this dot product is greater than alpha, so that's a positive number. Remember that these were 2 non-negative vectors. So you can try to exactly match them with the dot product of 2 non-negative numbers. But if this dot product was less than alpha, then this is a negative number. And basically, the best thing you can do here is just to set this dot product to 0. Right? So the representation is going to look like something like this, basically disjoint support of those vectors. Right? So that's what this is referring to. And here is the, all right, so this is what the cost function is doing. So what does this have to do with the local network that I just described to you? Right? So now I've been telling you that this has something to do with Hebbian learning, and let's do this explicitly. What I'll do is I'll try to start from this cost function and come to this particular neural network that I described that has Hebbian learning in it, and I'll show that that's actually doing a gradient descent on this. Okay? And to do that, I'll do one simple trick because of the following. So one thing you see here that there are no weights. Okay, so I'm optimizing, learning is about learning the weights. There are no weights here. So where are they? And I did not assume a particular network yet. Network is going to come out of it. So it's not like deep learning. I didn't do anything of that sort yet. To make that explicit, I'm going to do the following. I'm just going to expand this square. That's it. Right? So I just took this, expanded this square. There's a term that depends on x, which I just ignored. And I got with basically these, this term over here. Another thing I did is I actually changed the orders of, I moved one of these summations inside. And so this is the same thing. I just took this t prime sum, put it inside. There's nothing, no big deal over here. All right. After I write this, I look into it and I see, okay, so these were about similarities, but these are like correlation matrices over here. And Hebbian learning is about correlations. So that's perhaps where the synaptic weights are hidden, right? And to make that explicit, here's what I do. I introduce two more variables, right, which are basically placeholders for these matrices, just basically duality. Right? So I claim that this whole thing, this whole term, is the optimum of this optimization problem, where I introduce the W matrix for this and a potential for it, meaning if I minimize this, respect to W, set to 0, I get an optimal value for it, plug it back, I get this back. It's very simple algebra, no big deal here. And I have the same thing happening over here, right? So L, I introduce an L for this matrix, okay? No big deal. But this does help me in something. When I put everything together, I end up with basically one big optimization problem. Now, one thing that happened is I had two summations over time that decoupled into one, which basically makes the problem easier to solve. Now it becomes sort of amenable to these stochastic gradient descent kind of ideas. So for each input, I'm going to solve this with gradient descent until convergence. Or, for each input, I'm going to do a gradient descent on W and an ascent on L. And to be able to do that, for each input, I'll find actually the optimal value of Y, plug that back in, and do that procedure. So this is called stochastic min-max gradient descent ascent. There are different names for this. All right. And that's basically where the connection to a neural network comes in. To be able to solve this, it's a quadratic optimization problem. Of course, you can do many things, but one way you could do this is exactly solve it by the dynamics of such network. So you can prove actually that this is a Lyapunov function on such dynamics. Okay? And that basically sets what this W is and what L is. And the second step of this basically gives you the gradient descent and ascent on this basically gives you the plasticity rules for this. Right? And the thing I did here is I actually explicitly wrote the whole objective function, okay, in terms of the components of these x's and y's and w's. And this is the magic of everything I'm doing, right? So if you see what's happening here, although this was the original thing was a complicated thing, here the potentials for each of these synaptic weights are local in the sense that Wij, or the potential for Wij, depends only on itself, its input and output. So in modern jargon, right, the credit assignment problem in this network is solved in an explicit manner, where all the credit is assigned, or the whole objective function is basically divided into local objectives for each of these synapses, which means which I take a derivative, I end up with this Hebbian and anti-Hebbian learning rules. So this is just coming from a derivative of all of this. And that's basically the whole thing again, right? So this was a network. I showed that this is coming from a gradient descent of an objective function, so it's actually efficient, and it basically optimizes this cost function. And here is the same thing in action. So it's a simple data set, just has 3 alpha clusters in it, right? I give it to the network, I run it after many iterations. I look at the merge representations. So here is the blue alpha cluster, here is the red alpha cluster, and here is the blue-green alpha cluster. And as promised, you're seeing that like only a bunch of neurons are responding to some things, and only another bunch of neurons are responding to other things. So they're really disentangling these subspaces in a very explicit manner. I'll finish in a few minutes, okay? You're seeing another thing. Within one cluster, you're seeing that these neurons are actually not responding to the whole neighborhood, the whole data set in a distributed manner, but they're responding to their localized neighborhoods, okay? So this is not a manifold learning in the machine learning sense where you're trying to learn a low linear dimensional representation of the whole manifold. It's actually the opposite of it. You're learning a representation that's like for units that respond to localized neighborhoods. So in terms of linear dimensions, a very high dimensional representation. That's interesting because this is actually how brain represents manifolds. So there's a famous Nobel Prize winning work in so-called place cells. This is basically how the brain represents space, two-dimensional flat manifold. It's exactly of this sort. So you will find neurons that respond to localized neighborhoods. It's not like we have a one X neuron and one Y neuron. It's actually this way. Okay, so, and there's some theory of it which I'll skip. But so it's another example of this. So what you're seeing here is now a circle in some high dimensions. Each frame here is basically a teapot. Right? So in high dimension, it's basically a periodic thing. So what goes into this network is each frame, and I produce an output, and that's what I'm plotting over here. So x-axis is the angle of the frame, and y-axis are neurons. All right? And what you're seeing here is that, again, neurons become selective to particular teapot orientations. So they only fire when this guy is firing only when the teapot is oriented this angle, but nothing else. And this basically can, in realistic data sets too, if you give MNIST, you'll find that neurons are responding to localized neighborhoods of zeros, or spheres, or two-dimensional grids, and so on and so forth. Okay, so there's a theory behind this which was published in NIBS, so I'm not going to go in this. What I'm just going to tell you is all this was about basically single circuit, basically one module. So what I've been doing recently was trying to see how you can build like modules both within a layer and across layer to do these things. Okay, because I'm running out of time, I'll skip the theory of it, but I'll show you just simulation results. So basically, the idea is you can actually build in a theoretically oriented sort of a principled way. You can write cost functions where you can introduce multiple layers of such Hebbian and anti-Hebbian neural networks, and you can introduce actually spatial structure or topography to these things, such that when you give it like data sets, realistic data sets, they actually learn meaningful features. This is just a simulation example. The data set is faces, all right? So what you're seeing here is multiple layers. The first layer is basically looking at little patches. And if you zoom in, so each little square is a feature learned by a neuron in this first layer. And they become basically an eyebrow bank. If they were looking into the other patch, they'll become a mouth bank, and so on and so forth. The second layer combines them and learns basically a larger sort of feature bank. And third layer becomes more holistic, and so on and so forth. The point of all of this was all done without backpropagation, all Hebbian learning, and that's it. Okay, so to summarize, Hebbian plasticity actually performs similarity-based manifold learning and disentangling, and it actually performs gradient-based learning, saying maybe one more thing I'd say. So that the brain may not be doing backpropagation doesn't mean that it's not efficient. It's just efficient on a different class of problems, and that's maybe what we should be all looking for. All right. Thank you. Then these are the people whose work went into the slides that I present. Thanks.
Okay, something. Any question?
So, Cengiz, about this non-active dimension reduction. Non-active dimension reduction. Is there a way to understand convergence of this algorithm? You presented one algorithm.
Yeah. So the algorithm I have is I have an analysis which is sort of an approximate one. So basically, what you do is a dynamical system approximation to the dynamics of the synaptic weights. It's called stochastic approximation in ancient literature.
Yeah.
And I show that its fixed points are the things that you wanted them to be. So basically, fixed points are linearly stable only if they are corresponding to projecting the data into the principal subspace. So that's the one analysis that I have so far. But I don't have like an online learning kind of analysis for these kinds of things.
If I try to incorporate the biologically inspired mechanism into an artificial neural network,
Sure.
and in terms of this similarity machine code function, the training, obviously it speeds up my optimization because I don't need to compute all these long-range gradients. But at the same time, would it take longer for me to reach optimum? Because
That is a very good point. It will take longer, and there's a reason you're seeing Intel here, it's because of this point. It is true. So because basically you're replacing backpropagation by recurrent dynamics, so neurons can talk to each other, right? So you don't want to do okay. So that's a problem. Okay, but this problem is not. It turns out this problem is also a problem for industry, where people are building these neuromorphic chips. So Intel is building one, and these units on these chips are supposed to be like processing units are supposed to be like neurons, and they operate with such kind of architectures, and their learning rules are local. They can't do backprop in an obvious manner, right? So the problem appears over there too. But it turns out in spiking versions of such chips, you can actually simulate them very faster because everything is happening on the hardware, right? And this recurrent dynamics convergence issue becomes a non-issue, just too fast. So in such environments, it works. Actually, that's exactly what a student of mine is trying to do, port all of these to such simulation environments and see how fast they can be. But what you're suggesting is true. Right. There's another way around it, which is the following. I don't know how much time I have, but in all of these, I assume that the data are just coming from IID from something. But in real life, they're coming from some temporally correlated distributions, so they're not changing too fast, meaning that if you're in one equilibrium point and the next input comes, you're not going to go too far away from that equilibrium point. So the internal dynamics will have some time to, it doesn't have to run a whole new thing to get to that equilibrium point. It's going to be close to the original point it was. Right.
Okay.
Thank you.
Thank you. And welcome to our second speaker. Thanks to the topic is modeling economic time series using deep learning.